You're probably wondering how I got here and what the heck is going on. I'm Tony White, an applications engineer at Blue Robotics. I'm a part of both the product experience and research and development teams. So besides working through typical user experiences, I also get to test all the cool new tech our team builds, plus gear from other amazing companies destined for the Blue Robotics reef. I've been using Blue Robotics hardware for more than 10 years across different jobs, and for the last 2 years, I've been lucky enough to be part of the team full time. Our mission is simple: enable the future of marine robotics. We want to make it easier for anyone to discover, create, and innovate. We do that with modular components, open source software, full technical details and 3D models, and clearly communicated prices that keep everything as affordable as possible. I'm excited to provide this video to address the Marine Technology Society's TechSurge event with my story of AUV development, and hope those attending or coming across this video later are inspired to go forth and solve problems in the marine world, particularly when they challenge the status quo. Let's go back to the start of this tale. I'm based on the Big Island of Hawaii and was out testing one afternoon when I got a message from a friend. Gavin Key is a key member of Oceanera, which is a startup focused on pioneering aquaculture in federal waters and on the high seas, growing both fish and macroalgae. One of the most important planning steps for any offshore project is a site survey, and if moorings are going to be involved, a good understanding of the bottom type is critical in selecting the right anchor. I'd seen a lot of user curiosity around AUVs over the years and thought a project to capture imagery of the bottom would be a great demonstration of just how straightforward it can be to build something to take good video without breaking the bank. And so, the unique AUV you see here is what I'm calling a VP AUV, a vertical profiling autonomous underwater vehicle. The final design will soon be published for anyone to build and modify, and I'm excited to give the MTS TechSurge an early rundown. So you might be wondering how one goes about creating an AUV, designing, programming, testing and simulation, and then reality, all as cheaply and quickly as possible. And my answer, our answer at Blue Robotics, is with an extensive library of subsea components and open source software. I chose a 3-inch enclosure. Any smaller and I couldn't fit our standard 4-cell battery, and the depth rating was more than sufficient for our initial goals. From there, it was just a bit of 3D printing and wiring of standard Blue ROV2 and Blue Boat components into the enclosure with a USB low-light camera in the nose and a Pi 4 with navigator stacked behind it. The system thinks it is a standard 6-thruster ROV, but only its 2 vertical thrusters are actually connected. This makes the use of a Lua script, acting as the boss of the autopilot, very easy to develop and test in BlueOS's built-in software-in-the-loop simulation environment. The whole control script was vibe-coded in no time at all, and the inevitable errors worked out via the simulation testing and AI review of error messages. By February, the first prototype was ready for testing. The day started out with some excitement waiting for the local submarine traffic to clear at the Naked Lady sailboat wreck. Then the profiling AUV descended to strike the bottom at 100 feet, and I made the mistake of thinking everything was working. But as we all know, things rarely ever work perfectly the first time. That's why we test. Things were going great until the autopilot entered altitude hold to hover near the bottom, at which point everything went crazy. It would turn out that while the Lua script motor directions were correct, the left and right channels were swapped, and so the autopilot's efforts to stabilize itself were having the opposite effect. The 2 control signal connections could have been physically swapped, but making the quick change on the BlueOS vehicle setup page let me keep things sealed up. Subsequent shallow tests showed the vehicle was working well. We deployed in a deeper area, observing lots of halimeda at 70 meters, a flourishing green algae, and even a few starfish hanging around. You can tell the current is really blowing by the rate at which the vehicle drifts over the terrain. Satisfied we had a robust system, it was time for the big test, checking out the bottom at 400 meters. The prototype was launched and a stopwatch started. The vehicle zoomed downwards, passing 100, 200, 300 meters while we waited, clueless at the surface. After about 120 meters, ambient light wasn't sufficient for the camera to see anything. Internal air pressure increased as measured by the barometer, and the temperature fell. Of course, waiting at the surface, we had no idea how things were going. The vehicle could leak, or if the foam crushed completely, untested code and stability would see the vehicle trying to reverse its way home. It was quite gratifying when the vehicle returned to the surface within 15 seconds of when it was expected, less than 100 meters from the launch point. It was clear on recovery that the R3318 foam, even coated, was properly rated, and that rating had been exceeded. The data was quickly downloaded and reviewed. At exactly the expected depth, the recorded video showed the vehicle struck the bottom. Boing! The system hovered for the next 2 minutes, slowly increasing the lumen light brightness until the max output of 2000 lumens was achieved. The lights coming up gradually gives the volcanic rock and sand coming into view the vibes of an alien world, like a landing on a distant moon. I had the lights do this to better understand what a good level would be at extreme depths. I didn't want to overpower the sensor or have too much backscatter, but definitely enjoyed the resulting spooky effect. The test was a success, in spite of the foam being partially crushed by the extreme pressure, and I was hungry to share the design. But a problem remained. Users wouldn't be able to build what I had, as it used an extended flange from a forgotten project that isn't available in the Blue Robotics catalog. And so version 2.0 came together quickly with the primary goal to make sure anyone could reproduce the hardware. A water sampler from our friend Peter at Pragmatech also needed some testing, and to catch it in action, an Explore HD camera was installed alongside to provide a cool third-person perspective on the vehicle's operations. Water samples at different depths are very valuable for nutrient analysis and understanding the dynamics of a potential algae farm site. This time, the guts were held together with the new rails and only 2 small printed parts. They made the internal layout system really awesome, living up to their acronym. More hardware was added to test, including the RadCam and IP camera destined to supercharge the standard Blue ROV2, and a Pi 5 with updated navigator. Both are exciting upcoming products. The vehicle is now one long tube, with a coupling flange prototype being evaluated prior to its product launch. Changes to the Lewis script to provide water sampling dive controls were the easiest part. I roped in a couple friends for a shore dive, and we swam the AUV out to send it on a mission, stopping every 5 meters. Once again, the first test proved not to go as expected right when the vehicle switched to hover. The same issue that had impacted the first version had been forgotten. I corrected it and was out the next day. Things appeared to be fixed, but appearances can be deceiving. The vehicle was now stable and able to hover, but when it finished the first water sample at 5 meters, it didn't proceed downwards, instead going up a few meters to hover for another couple of minutes. While the new script worked in simulation, the descent rate didn't change as fast in the real world. A grace period needed to be added to help the state machine proceed as it should. With deadlines for TechSurge rapidly approaching, a final chance to test the vehicle remained. While we watch it in action, I'd like to wrap up this video presentation by describing our future goals for this vehicle. A detailed guide will be published on the Blue Robotics website that will cover how to build your own profiling AUV and program it for your own unique applications. Things like the bill of materials, controlling Lewis script, and video recording extension will all be included, alongside the 3D CAD data and assembly and setup instructions. Of course, this is all mostly public on GitHub already, just not explained thoroughly. In terms of future development, I'm excited to integrate a stereo camera payload, employing it to recognize the bottom to avoid ever touching it. Drifting photogrammetry in conjunction with acoustic tracking may be interesting, and profiling of the water column with various sensors likely has the broadest appeal. I'm excited to see how the fisheries, benthic monitoring, and aquaculture community as a whole might use devices like this. I shared plans on the Blue Robotics forums for a T500-based diver propulsion vehicle, and in less than a year, over a dozen groups worldwide have built their own. As the footage shows, some tweaks to RadCam control to ensure the picture is in focus, as well as adjustments to the behavior of the vehicle post-dive are still left to do, but overall, things are now mostly working. I hope this video has helped inform you of all the possibilities when you're building with Blue Robotics. In both software and hardware development, building with pre-existing solutions can not only speed things up, but make your creations modular and easy to adapt to varying challenges. If you don't consider yourself particularly technical, that shouldn't be a barrier to applying your creativity and solving problems in the ocean. Please reach out to me with any questions. We love inspiring diverse groups to tackle their marine robotics challenges. Thanks, and don't forget to like and subscribe.